This is Dr. Holt. This lesson is on potential energy and the conservation of mechanical energy. When dealing with mechanical energy and potential energy, we need to define the two types of forces. You have conservative and you have non-conservative forces. In looking at conservative force, the work done by a conservative force on an object moving from one point to another point depends only on the initial and final position of the object. It's independent of the particular path taken, meaning that the work done by a conservative force, it doesn't matter whether I start here at 1, I go all the way over to here, and back to here, or I go directly from here to here. The work done by a conservative force is going to be the same. It's completely independent of the path taken. So to highlight the important parts of conservative force is that the work in moving an object is independent of the path taken, and the work in moving an object through a closed path is always going to be 0. Meaning, again, if I get my pen out, and we'll do it in blue, if I move from here back to here, then the work done is going to be 0 that's being done by that conservative force. I listed here 3 types of conservative forces: gravity, electrostatics, and springs. When you're talking about non-conservative forces, the work is going to be path dependent, and the work done along a closed path is not going to be 0. And then the work is going to be related to the change in mechanical energy or thermal energy. Examples would be friction, drag, push or pull by a person, or we're talking about motor or rocket propulsion. Here I've defined in more depth conservative forces and non-conservative forces. When you talk about conservative force, it's dependent only on the position of the object. And when I move an object from one location to another, then the force changes the potential energy of the object. And this is important to know when you get into the conservation of mechanical energy. Again, if the force is non-conservative, then taking different paths will lead to a conflicting potential difference between the start and end points. Non-conservative forces, they transfer the energy, and the energy is going to be transferred back into like heat or sound. Potential energy. When a ski lift raises you to the top of the hill, the ski lift itself is going to do work of being mgh. The mass of the object times gravity times the height is being raised, and that work is being done on you and the Earth system. This work is going to be stored as gravitational potential energy of the Earth system. When you ski down the hill, the potential energy is going to be converted back to kinetic energy, which means your velocity is going to increase as you go down that hill. Note that when you ski down the hill, the work done by gravity decreases the potential energy of the system. And we define the potential energy using the symbol U. So when you see the symbol U, you're talking about potential energy. Here, I have a skier located here and here. Now, one thing to note, it doesn't really matter where you set up your axis where you want the potential energy to be 0. If I set up this position, this axis here being my 0, then in respect to this axis, the potential energy of this skier in respect to this axis would be the mass of the skier times g times this vertical distance being the h value. You do not want to let this be the h value. It has to be the direction, vertical direction from that axis or perpendicular to this axis. If I establish this position being my 0, then I could say this skier here has 0 potential energy in respect to the system. But when the skier gets down to here, it would be minus mgh, because the skier has gone negative an h distance in respect to this axis. So the skier has negative potential energy in respect to axis number x2. When you're dealing with springs, my advice would be to set the equilibrium point as your being x equals 0. If I compress the spring, then the potential energy is going to be 1/2 times k, k being the spring constant, times x squared, x being the deflection of the spring. That's giving me the potential energy of the spring. If I extend the spring, again, it's going to be potential energy, but the potential energy is going to be built up, which is going to want the object to move back this way here. In defining the equation for the conservation of mechanical energy, we look at the work energy principle, meaning that the net work is always equal to the change in kinetic energy. And we could say that it's going to be 1/2 m times position 2 being velocity squared, v2 squared minus 1/2 mv1 squared, or what we're used to is 1/2 mv squared, vf squared minus 1/2 v initial squared. Since there's conservative and non-conservative forces, then we can say that the work net is going to be the work done by the conservative plus the non-conservative is going to equal to the change of kinetic energy. Now we note that conservative forces are equal to the loss in potential energy. So we say the negative change in potential energy plus the work done by non-conservative forces is equal to the change in kinetic energy. Therefore, we can say that non-conservative forces, which is all I'm doing is moving this to the other side, is going to be the sum of the change in kinetic energy plus the change in potential energy, which equals to the change in energy. Now, if we let the total work done by external forces and all internal non-conservative forces being 0, as stated here, that all I'm doing is letting this be 0, then I go back to the change of kinetic energy plus the change of potential energy is equal to 0. As stated here, I substitute back in knowing that the change of kinetic energy is going to equal to final kinetic energy minus initial kinetic energy. I set this change of potential energy as final potential energy minus initial potential energy. And now all I have to do is move all these to one side of the equation and move all these to the other side of the equation, and I get final kinetic energy plus final potential energy must equal to initial kinetic energy plus initial potential energy. And this equation is considered the conservation of mechanical energy, and it's a very, very useful equation. The principles of the conservation of mechanical energy. If only conservative forces are doing work, then the total mechanical energy of a system neither increases nor decreases in any process. It stays constant, or it is conserved. Example here, I have a rock. I've lifted this rock up a certain height. Then what's happened is this rock has potential energy. If I release this rock, it's going to immediately start losing potential energy as it falls, but it's gaining kinetic energy. At the halfway point, the potential energy and the kinetic energy are the same. As it continues falling down to this axis being 0, I've lost all my potential energy only in respect to this line, and it's all turned into kinetic energy. However, I go back to the equation that final kinetic energy plus initial potential energy, final kinetic energy plus final potential energy is equal to initial kinetic energy plus initial potential energy. Okay, let's look at this problem here. I got a roller coaster here. It's top of the hill. This distance is going to be 40 meters. We want to find out what the speed of the roller coaster is going to be at the bottom of the hill, and at what height will it have half its speed. what you want to do with this problem here, I'm going to let this be my x-axis here, meaning the potential energy in respect to this axis right here is going to be 0. So I go back and I'm going to find out what the potential energy of the roller coaster is in respect to here. At here, potential energy is going to be mass times 9.8 times 40, and that's going to give me 392 m. And we'll make that be our initial. Our kinetic energy here at here is going to be 0 because our velocity is 0. So we go back to conservation mechanical energy, and we can say that the potential energy initial plus the kinetic energy initial is going to equal to potential energy final plus kinetic energy final. Scroll down, give myself a little bit more work, a little bit more room. We have 392 m, and again that's going to be plus 0 is equal to our potential energy down here is 0 because we have no height. We go back to kinetic energy, which is 1/2 times m times v squared. We're left, now the m's will cancel out, that gives me 392 is equal to 1/2 v squared. So now we can take 392, we multiply that by 2, and we take the square root of that, and that tells us that the velocity at the bottom is just going to be 28 meters per second. Alright, this is part B. It says at what height will it have half this speed? Alright, to find out what, we go back again, we can use the conservation of mechanical energy. We're going to again we'll let this be our initial position, and we're going to say this object only has well, actually, let's do it this way. We'll still let this be our 0. We'll just say we're going to find a point up here where the velocity is going to be 1/2. So can we not say, go back to again conservation mechanical energy, that mass times 9.8 times h, and we'll calculate what the kinetic is. That's going to be 1/2, and we're going to make that 14 because we got half squared is equal to, now down at the bottom we still have no potential energy, and we're basically going to put this back into here, which is going to give me, I'll do it, but it's going to give me 392 m. Okay, so that's going to give me 9.8. I can cancel out my m's because I get m's all the way across. We know that's going to equal to 392. Alright, so we'll calculate this one here, 0.5 times 14 squared. That gives me 98. So we got 9.8 times h plus 98 is equal to 392. We take 392, we subtract 98, we divide by 9.8, and we get h is 30. Alright, so we found out when h is actually 30, so when this object's gone 10 down here, the velocity now has reached 1/2 or 14 meters a second. So our answer here would be 30 meters. Okay, one more problem here. When you're dealing with spring potential energy, all you're going to do here is you're going to let your kinetic energy of the system plus the spring potential energy, again you're just doing the conservation mechanical energy, is equal to the final or position 2 if you want to call it this way. Call it that. Here we have a dart of mass 0.1 kilogram pressed against a spring pressed against the spring of a toy dart gun. The spring has a spring constant of 250 newtons per meter. It's compressed to 6 centimeters. Okay, so what you want to do is to find out the potential energy of that spring. We're just going to go back to 1/2 times kx squared, which would be 250. We change our 6 to 0.06. We square that. So 0.5 times 250 times 0.06 squared. That gives me 0.45 joules. Alright, so now if we want to find out what the velocity is going to be when this trigger is pulled and that dart gets to the end of the gun, it's lost all the spring potential. So we can just go back to 0.45. We can set that equal to 1/2 times the mass, which is going to be 0.10 times v squared, and calculate v. So I take 0.45, I multiply that by 2, I divide by 0.1, and I take the square root of that, and that gives me a velocity of 3 meters per second. And again, all you're doing on these problems is following the conservation of mechanical energy.